I'll be talking about the kinetics of food turning bad today. We're going to make a lot of approximations and assumptions. First, I'm going to assume there's something in the food. I'm going to call that X. The mysterious X reacts with oxygen and forms something really bad. I'm going to assume this is a second order elementary reaction. First order with respect to X. First order with respect to O2 over all second order. The reaction rate thus is the reaction rate constant K here times the concentration of X and the concentration of O2. The concentration of O2 in air is 0.008 molar, and then we can combine K and the concentration of O2. We say it's K prime, and again here I'm going to say K prime equals 0.008 molar times K. How did I get this number? So we do know that at the room temperature and 1 bar pressure, I think the concentration of air is 1 mole divided by 25 liters. Well, you just use PV equals RT, you can compute this. PV equals RT, and therefore N over V is equal to P over RT, so you get this. Is 0.04 molar. The concentration of O2 is 20% of that. The concentration of nitrogen is 80% of the concentration of air, but anyway, we're just talking about O2. Nitrogen is inert. Okay, so we got this number. That's why we got this 0.008 molar for O2. We're going to assume this concentration doesn't change throughout the reaction. So, again, I want to emphasize this. It's a second order elementary reaction, but because the concentration of one of the two reactants remains unchanged, we can combine this K and the concentration of that constant, the constant concentration here. We can combine this two. And then we can tell that the reaction rate actually depends on the concentration of only one reactant, and it's a first order reaction. We call that pseudo-first order because, again, in the elementary reaction step, there are actually two different reactants. Supposedly, you have a power here, another power here, you sum it up, or the order is 2. But only because this O2 remains constant throughout the reaction, we can tell that the reaction rate in the end is proportional to only the concentration of this X. Now I'm going to give you some experimental data. I collected some kind of food at different temperatures. The room temperature, you put the food on the dinner table, and it's 295 K. 2 degrees, 275 K. Negative 18 degrees, well, that's 255 K. All right, and I measured the half-life of the food. So half-life means, well, half of the food has turned bad. Half of the food has turned bad. How did I know that? Well, I estimate. Roughly 1 day here, okay? Roughly 10 days. Well, I have the unit here, so I just need to put 1 here, and 10 here, let's say 100 here. K prime. How do we know the K prime? Well, it's a pseudo-first order, and we do know the half-life is ln2 over K, in this case K prime. And K prime is simply ln2 over the half-life. ln2 is 0.693 over half-life. So I'm going to use 0.7 just for simplicity. 0.7 divided by this. Okay, 0.7, that's easy. 0.07, 0.007. Hey, we got the reaction rate constant here in the unit of day to the power of -1. We have a nice data table here now. Oh, actually, I was kidding, and I've never done the real experiments. I made up all those numbers. How do we analyze this? We know the reaction rate constant. I'm using K prime here just to remind you this K prime is actually K times the concentration of O2. So it's equal to A to the power of A times E to the power of activation energy over RT. Yeah, do not just plot K prime over t. You can not tell anything from the graph. It's just a bit too complicated. So we like linear relationship. Anything nonlinear, we convert it to linear. So we take the logarithm of k prime. And look at this. Look at this. And k prime is a linear function of 1 over t. So 1 over t here and here. All right, and now this time we have 3 data points. We can plot this. 3 data point 1, 2, 3. Okay, 3 data points. Well, it's not going to be linear, 100% linear, but so 1 over t, actually it's better to use 1k over t, therefore it's just a number. And the k prime, it's better to just say k prime divided by the unit of k prime, which is day to the power of -1. So basically it's k prime times a day here. It's just to remove the unit. Before we take the logarithm, it doesn't make sense to take the logarithm of a unit. So if I ask you what's the logarithm of 1 day, you may say 0, but then if I ask you what's the logarithm of 86,400 second, I mean it's really hard to answer that question, right? Because 1 day is equal to 86,400 seconds. All right, again, I'm gonna just assume that we did this linear regression. This part is going to be your L1A, again divided by its unit. So it's actually the intercept is actually L1A, the pre-exponential factor, divided by its unit. So you can see the A here, and the unit of A is also day to the power of -1, and you have a slope. You have a slope. This is more important, and the slope is negative EA over R. Over here, that's your slope. All right, so I'll let you work on this. You can use Excel spreadsheet, you can use Google spreadsheet, you can get the intercept and determine A. More importantly, you can get the slope from the graph, and then you can compute the activation energy. I'm going to hand calculate the activation energy here. To do that, I need to just pick 2 data points. It's more difficult to pick 3 data points and do the calculation. I'm going to pick this 2. There's a wider temperature range here. And what I would do is, again, I will start with the Arrhenius equation. So I have k prime at 22 degrees Celsius is equal to A to the power of -EA divided by RT. R is here. T is, again, we'll have to actually use Kelvin here, 295K. So this guy is equal to 0.7 day to the power of -1. That's my first data point. My second data point is 0.07 day to the power of -1 is equal to A e to the power of -EA over R times 255K. Lower temperature, really cold. Okay. That's my equation 1. It's equation 2, and I'm going to use equation 1 divided by equation 2. Obviously, this divided by this. I'm sorry, there's another 0 here. You get 100. Why do I do this? Because A divided by A, it's just 1. R is the Avogadro constant. All right, and then we'll take the logarithm of both sides. The logarithm of 100 is, I think, 4.605. The logarithm of the right-hand side is just, I I'll swap the sign here inside, so it's going to be the activation energy divided by R. You might have noticed that I did not write the unit here because I'm using the SI units for the entire reaction. So basically this EA will be a number in the SI unit or derived SI unit in the end. Over here, I don't know. I mean, it's just it's going to be 1 over 255 minus 1 over 295. So I think it's something like this. On the bottom, again, I don't know what this is, but it's roughly 300 times 250. So it's probably roughly 75K. But anyway, you got this nice equation here. Look at this. There's only one variable in this equation. There are a bunch of numbers. We just need to do the numerical calculation here. So I'll do that here. I'm going to erase a part of the table. Okay, so E sub A is going to be 4.605 times 8.31446. That's your R times 295 on top, 255 on top, 295 minus 255, 40. Okay, so it's I'm not gonna really calculate this, but I think this is roughly 5 times 8, 40, a bit lower than 40, a bit smaller than 40. So this is 75K, so it's a bit lower than 40, this is 40. So it's going to be smaller than 75K. I'm going to say 70K. 70K. And again, the unit is the derived SI unit is joule per mole, and we commonly use kilojoule per mole in this situation. It's roughly 70 kilojoule per mole. It tells you the activation energy for your food. Reacting with oxygen and turning bad is roughly 70 kilojoule per mole. This is roughly 3 times the hydrogen bonding energy in water. This is roughly 1/6 of the carbon hydrogen bond energy or oxygen hydrogen bond energy.